I thank you all for watching my video and encouraging me. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. Thank you. We now discuss the solution of a problem that appeared in the CSIR National Eligibility Test held in the month of June 2023. This question is from group theory and it is related to a group of order 2023. This question is from the part C, which is a multiple select question. There can be more than one answer and it carries 4.75 marks. The question ID is 704084. This question is suitable for all these examinations. Right. The given question is, let G be a group of order 2023. Which of the following statements are true? We are given four options. Option 1, G is an abelian group. Option 2, G is a cyclic group. Option 3, G is a simple group. Option 4, G is not a simple group. Let's now discuss the solution of the problem in detail. We are given a group G whose order is 2023. The prime factorization for 2023 is 7 into 17 square. Right. Now, we talk in terms of the divisibility. The prime number 7 divides 7 into 17 square and 7 square does not divide 7 into 17 square. So we recall the first theorem of Sylow. By Sylow's first theorem, G has a Sylow 7 subgroup. Let's call it as H of order 7. Go to 17 now. 17 square divides 7 into 17 square and 17 cube does not divide 7 into 17 square. Again, by Sylow's first theorem, G has a Sylow 17 subgroup capital K of order 17 square. Agreed. Now we will count how many Sylow 7 subgroups of order 7 are there. To count them, N7 denotes the number of Sylow 7 subgroups of G, and it is of the form 1 plus 7k, and N7 divides the order of G, that is 7 into 17 square. That is 1 plus 7k divides 7 into 17 square. This is by Sylow's third theorem. This implies N7 is 1 plus 7k divides 7 into 17 square. 1 plus 7k does not divide 7 at all. So that 1 plus 7k divides 17 square. So, and for what values of k, 1 plus 7k divides k square. For k is equal to 0, 1 divides 17 square. Yes, k is 0. For k is equal to 1, 1 plus 7, 8. 8 does not divide 17 square. For k is equal to 2. 2 7s are 14 plus 1, 15 does not divide 17 square. And k is equal to 3. 3 sevens are 21 plus 1, 22. And it does not divide 17 square. Going on like this, we will find k is equal to 0 is the only solution for this. So k is equal to 0 means 1 plus 7k becomes 1. That means n7 is 1. That means there is exactly one Sylow 7 subgroup h of order 7. That means there is a unique Sylow 7 subgroup h of order 7. So recall a theorem which says that a Sylow P subgroup of a finite group G is a normal subgroup of G if and only if it is the only Sylow P subgroup of G. So here n7 is equal to 1 means it is the only Sylow P subgroup of G. Therefore, by this theorem, it is that subgroup, that means the subgroup H of order 7 is normal in K. So H is normal in G, not K. H is normal in G. So we have a normal subgroup. Now, thus G has a non-trivial, because its order is 7, normal subgroup H. So recall definition of the simple group. A group is a simple if its only normal subgroups are the identity subgroup and the group itself. That means the trivial subgroups are the only subgroups of a group, then that group is said to be simple. But we have G has a non-trivial normal subgroup H, therefore G is not a simple group. Now call on option 1, option 3, which says G is a simple group, which is not true. Option 4, it says G is not a simple group. Yes, it is true. So thus, option 3 is not true and option 4 is true. Right. So we move on to the next slide for the further discussion. So before that, arguing similarly, what about n17? N17. We get n17 is equal to 1. Similarly, you argue, and thereby you will find K is a normal subgroup of G. Agreed. Now, so far we have proved that G has normal subgroups H and K of orders 7 and 17 square respectively. Now, what is H intersection K? The intersection of two subgroups is again a subgroup. H intersection K is the identity element alone. Why? Because the GCD of order of H, order of K, that is the GCD of 7, 17 square is 1. Therefore, the order of H intersection K will be 1 and thereby H intersection K is identity element alone. Thus, what are the properties what we have now? So now order of HK. What is order of HK? It is called complex. Order of HK is equal to, remember the formula, order of H multiplied by order of K by order of H intersection K. That is equal to order of H is 7 into order of K is 17 square by order of H intersection K is 1. Now 7 into 17 square is 2023, that is order of G. Now what is HK? HK is a complex and HK is a subgroup of G and the order of HK is equal to order of G, which will compel you to say that G is equal to HK. So what are the now properties? The properties are 1. G is HK. 2. H and K are normal subgroup G. 3. H intersection K is identity element alone. So now, what can you say? We say G is the internal direct product of H and K that is G is equal to H cross K. But again, you remember another theorem. G is equal to H cross K, that is the internal direct product of H and K. Then G is isomorphic to the external direct product of H and K. Yes. This implies G is isomorphic to the external direct product of H and K, which is written as H plus circle K. Read it as external direct product of H and K. Agreed. Now we go on to the next slide, and this is what so far we have done. G is isomorphic to the external direct product of H and K. Now what is H? The order of H is 7. 7 is a prime. Every group of prime order is cyclic. Therefore, H is a cyclic group of order 7. Therefore, it's isomorphic to Z7. So now H is isomorphic to Z7. Since H is cyclic group of order 7, which is prime, and every group of prime order is cyclic, and we also know any two finite cyclic groups of the same order are isomorphic. H is cyclic, order 7. Z7 is of order 7 and it is cyclic. Therefore, they are isomorphic. Agreed. What about K? Note that K is abelian. How do you say? What is the order of K? 17 square. What is 17? It's a prime. That means it's a group of P square, where P is 17. And we know every group of order P square, where P is prime, is abelian. Thus K is abelian. So therefore G is isomorphic to the direct product of two abelian groups H and K. And the direct product of two abelian groups is again abelian. This is known to us. Therefore, this is abelian. And by this, you will get G is abelian. That means any group of orders any group G of order 2023 is abelian. This is over by this time only. To answer whether it can be cyclic or not, we have to extend our argument. Now, K is an abelian group of order 17 square, and all abelian groups of order 7 square. Then what are the possible direct products of K? They are K is isomorphic to Z17 square, and K is isomorphic to Z17 plus circle Z17, and K is isomorphic to Z17 square corresponds to the partition of 2 written as 2 plus 0, and the partition of 2 is 2 written as 1 plus 1, that corresponds to Z7 plus circle Z7. So there are only two partitions for 2. So for the corresponding to these two partitions, we get the direct products written like this. Right. Now, thus, up to isomorphism, we have two groups of order 2023. In the above, whatever they are, every group of order 2023 is abelian. That is true. Up to isomorphism, how many groups of order 2023 are? Two groups are there. What are they? 1. G is isomorphic to Z7 plus circle Z17 square. That is first one. Now see, 7 and 17 square, they are relatively prime. Their GCD is 1. Therefore, it is written as Z 7 into 17 square. And recall a result, Zm plus circle Zn is equal to Zmn if and only if m comma n is 1. So this is Z 7 cross 17 square, that is Z 2023. It is cyclic group of order 2023. What is the second one? G is the direct product of H and K, that is isomorphic to the direct product of the subgroups, direct product of Z7 plus circle Z17 plus circle Z17. For K, Z17 plus circle Z17. This is the second possibility. And 7 and 17, they are relatively prime. Therefore, Z7 plus circle Z17 is Z119 plus circle Z17. It's abelian. We have already seen G is abelian. But this is not cyclic. How can you say that this is not cyclic? The highest order of any element in Z119 plus circle Z17 is 119 only, 119 only. You cannot find an element of order 2023 in this. Therefore, it is an abelian but not cyclic. Right. Now, colon. In any case, every group of order 2023 is abelian, and one is cyclic and the other is just abelian but not cyclic. And let's look at our options. Option 1, G is an abelian group, correct? Option 2, G is a cyclic group, not true. It's not true. Thus, option 1 is true, option 2 is not true. Right. Summarizing all the options, the answer to this question are options 1 and 4. Option 1 here, 4 in the last slide. It is not a normal, it's not a simple group. That's the option 4. So that is the detailed discussion of the solution of the problem from the section Algebra, which is related to a group of order 2023. It is definitely a very interesting question and a very good question. But in the examination hall, so many theorems you have used in this, and it looks to me is difficult in the examination hall. But after coming out, you may say this is easy. Anyway, I am sure that you have understood the solution of this problem. Thank you for watching this video now. Please like my videos and share them with your friends and colleagues. Please subscribe my channel if you have not already subscribed. We will meet once again in another episode of learning. Enjoy learning mathematics. I wish you all the best. Thank you.